I'm Fabio Cinti, and I'm coming from Florence University. And in this 30 minutes, I'm trying to talk about bosons generically in geometry that usually people don't think about, or that perhaps experiment starting to come up in the near future, I hope. So first, I have to say thanks to all these smart guys that are working with me in this subject. First of all, Matteo Ciardi, who has just submitted his PhD thesis with me, and the next month will start his first postdoc with Thomas Paul in Vienna. So he's a very brilliant student, so I hope that you will have the chance to talk with him. And then, of course, there is Tommaso Macri here that work in many data that I'm going to present. Probably the picture is still fine, even if it's a bit old, right, Tommaso? It's okay. So you are still young, even in the reality. And then about the first part of the talk, I have to mention Vinicius, which started a few weeks ago a postdoc with us in Florence, and then also Alejandro Mendoza Cotto that is working with us on things related to quasi-crystal, and then also Fabio Mezzacapo and Adriano Angelone. They are both Italian, but they are located in France. And then regarding the second part of the talk, I have to mention Giuseppe Pellicane and Santi Prestipino that work in Messina. So all these people contributed the result that I'm going to talk about. The outline, so there were two subjects that I want. One is the thing that we call quantum quasicrystals, and the other one is the supersolidity on spherical surface. So I hope to have enough time to present both results. In the first part, I would like to show you what is the property of boson in these quasi-periodic lattices, and trying to understand if the Bose-Glass phase can be found even without the introduction of disorder or local disorder. The other subject is connected to supersolidity on surface, so on spherical surface. So the main idea is trying to understand the many-body physics on curvature. So, and here I show you a boson tangle with the quantum Monte Carlo on surface. And also I will try to take a possible experimental example with like the dipolar system. So let me try to start at the beginning of our work with Matteo and Tommaso. Our first idea was trying to study and understand the experiment made by a group in Cambridge, where they tried to cross laser in order to form a quasi-crystal structure, so this shallow lattice. And as you can see, the local disorder is created locally depending if you go on this direction or that direction, for instance. And our result simply says that moving V0, which is the potential the V0 in front of our quasi-crystal structure, we can go from a perfect superfluid phase to a region where this result are for T that goes to 0. So we are essentially in the ground state, very far from the transition temperature. And another region where essentially we have a Bose-Glass due to this disorder, where compressibility and superfluidity are finite. And then, of course, starting to increase again and again V0, we go to a perfect insulator, okay? So if you go to the diffraction pattern, the maximum are white here, you see, we can distinguish going around this angular boson density among these three phases, okay? In this case, maxima bosons are located around here, for instance, and they show connection between themselves. So it means that here we have superfluidity in this region, as well as in the region where I have this blue cycle. And again, I can distinguish between superfluid phase, the superfluid puddles of superfluidity, which is related to Bose glass, essentially, to a perfect insulating phase. And this is working very well, even at finite temperature. So we can try to come up with a nice phase diagram where we have superfluidity, Bose glass at finite temperature, and also insulated phase. So this, it makes sense because I have to deal with a system that has local disorder. So the next step is, what if I remove the local disorder? And what if I consider a pure lattice system with an approximation that is called Hamann-Benken tiling, which is the way to compose our quasi-crystal in space with open condition. What's happened if we work with quantum Monte Carlo in this kind of structure, and then this is the main Hamiltonian that we have. So, and the interaction on this side are different neighbors, okay, because the structure doesn't have the periodicity. So depending where the boson is located, can talk differently with the neighborhood. And we choose this kind of potential that try to simulate this condition, and we have an infinite term for epsilon smaller than a certain value, in a way that we can have only one bosons per site, okay? So in this way, we have a nice phase diagram, which is obtained on lattice, as I said, using a grand canonical ensemble, and we can distinguish mainly between two phases. The first one is basically a condensate phase, you see, with this blue region, moving V, the potential, and the chemical potential. And then we get into another phase, which is still, again, a Bose glass. So my idea is trying to show that it's not necessary to introduce the disorder, but it's just the quasi-periodicity that can give us the Bose glass phase. And how this is done, essentially, using quantum Monte Carlo. We study the condensate fraction by the one-body density matrix, and we mainly diagonalize in order to obtain the condensate fraction. And then we have to study compressibility, and then also using the so-called Ewald-Anderson parameter, we try to understand where there are regions of periodic structure that I will show you now. So let me comment this phase diagram, because I think it's very much important. So for small v and small chemical potential, essentially, we have a completely delocalization of the particle, and even the condensate fraction, so reach a finite regime at low temperature, and also compressibility seems works well. Increasing again the potential and the chemical potential, we get into what we call Bose glass phase, and we have this wheel structure that is an 8-4 rotational symmetric group made by the lattice, and inside these wheels, essentially particles are delocalized. Okay, so one important thing to talk about Bose glass is essentially that the total condensate fraction goes to 0, increasing the size of the system, and the compressibility is finite, again increasing the system size. Okay, let's analyze this Bose glass phase. Of course, if we go and look the word lines inside these wheels, we see that remain localized inside this 8-fold symmetry. So it means that there is indeed delocalization with respect to word lines that are completely straight. It means that in the quantum Monte Carlo language, we have essentially a crystal, or we are at a temperature high enough to don't see any quantum behavior. Okay? But another important thing, and here I have to spend some time about this slide, is that I would like to study the global density modulation parameter that give us the inhomogeneity of the imaginary time average site occupation. It means that this guy, essentially, it's some sort of language that comes from glass phases, that this Q parameter must be 0 if there is delocalization, and must be 1 if the system is insulator or even classical. And if we do the same idea inside each wheels, and we work on an histogram on this quantity inside the wheels, we still have that in the condensate, this guy is mainly mainly a maximum at 0. On the other hand, in the Bose glass, this histogram start to stay inside the wheel at the peak at equal to 0. Okay, here. On the other hand, if I increase the temperature, this parameter show essentially a peak at value that goes to 1. So it means that the structure start to be more and more classical even inside these wheels. We have another interesting phase which are not able to distinguish between with the condensate fraction, and we have this modulated phase which show finite condensation. We cannot call about supersolidity or something like that. And this can be evaluated using something that is similar to the previous parameter, but instead of using the quantumness of our path inside each side, we use the average density, okay, which is different and give us information about the modulation of the system, okay. And this parameter is increasing here, the red points, when I increase the chemical potential, keeping V fixed, okay. So and when it reached to a finite value around here, we still have condensation, okay. So we have this modulated phase in this quasi-crystal structure, which has indeed condensation, okay. So it's a very, I think, interesting model. So outlooks. We of course continuing study different interaction, dipolar interaction, and also study the system in cavity. And for understanding our work and what we are doing, I suggest to see the Vinicius poster about a dipolar system versus quasi-crystal structure. So I think that also in this case, there are very interesting results that are coming up, that we are ready to submit an article, but I would like that Vinicius explain you this new result. Okay, good. So in the next 15 minutes, I change the subject, and I want to talk to you about boson on spherical surface. From an experimental point of view, there are a lot of interesting things to say about this subject, because apparently people, they are able to create these shell-shaped traps using a quadrupolar field. I mean, it's something very experimental. I haven't well understood the idea, but throughout some adiabatic process, they are able to create these elliptical traps where they can confine bosons in this structure. The problem is that if you confine on the Earth, all boson fell down on the bottom of your trap, And so there are some experiments that have to be bought on the space station in order to study this kind of system in microgravity. And when I read this experimental articles, I wanted immediately to do quantum Monte Carlo with these bosons in order to understand the physics that can come up with this kind of system. With Luca Salasnic and Andrea Tononi, we start to study these elliptical traps, and we simply study the Bose-Einstein condensation as a function of the number of particles, and also about on the detuning of the structure. Okay, so and we did this already 3 years ago, but the idea here is try to introduce. This was made with just only contact interaction, so without considering any long-range interaction or any kind of interaction that gives you clustering. So in this physical model, instead, with Santi Prestipino and Matteo Ciardi, we introduce an Hamiltonian that has a sort of long-range interaction on a sphere. So studying essentially the two kind of model that usually are used. So soft core interaction, essentially related to the Rydberg dressing, even though, I mean, it's quite difficult to make a many-body system made of purely boson in a Rydberg context, but is an interesting model. We studied with Tommaso many years ago in Dresden, and so it's important. And the other model, which is more important for experiment, is the dipolar interaction, is an anisotropy interaction, and with quantum Monte Carlo we control the attraction with essentially a potential that is related to the scattering length of the system. Okay, so if you don't know, it's a system quite simple. We work in a spinless with spinless bosons. We don't have the code for fermions, but at finite temperature it's quite difficult to find something on the market. But and then in a canonical ensemble, in this case, and this lambda is h bar square over 12. So is the simply kinetic term in front of the Hamiltonian. So clustering in general is a very broad class of potential and is used both in soft matter, is very well used, and there is this famous article by Likos that explains simply one thing. If we have a generic potential like this, like a soft shoulder or something strange, but if its Fourier transform is as a minima at lower than 0, that gives the periodicity of the potential of the structure, we have clustering. Okay, and this has been studied in both in soft matter and in quantum system. Okay, so this is the main idea of clustering, and we want to put this clustering on surface. And the potential that I put here is the potential that they try to use in the real experiment. Essentially, we have this function, okay, and with U0 is the harmonic potential without this bump. And if U0 is strong enough, we have a small oscillation limit where essentially here we have our sphere on real two dimensions, okay? And it's quite interesting because they are able to produce this in a real experiment. So let me talk a bit about the Monte Carlo sampling. The problem is that here I have a continuum system, so I have world lines of boson that are tangled throughout the system, and in the cortex of this structure, I have the problem that many trial movement, many Gaussian trial movement are completely rejected. And what we have to do is try to bias the path integral Monte Carlo in a way to shape the Gaussian on the surface, okay? Just working on the standard deviation for the polar angle and the radial component of our sphere. And what we have, if in a weak confinement, so with this U parameter small, put equal to 2, we have the structure that of bosons that delocalizing the system in this, let me say, thick cortex or bark. But in the strong confinement, our Monte Carlo is able to study bosons indeed on a curved space, on a sphere. You see, they are quite well defined on a sphere that we can control. These are delocalized particles, okay, in the system, and I show you that some configuration that Matteo prepared for me from our codes, and we are able to control bosons that can percolate, they can go up and down inside the sphere, you know, and so it works quite well. And another important thing that I have to say, and that in the next time, in the time that remain, I will present superfluid results. And the superfluid results, using the idea of Sepperli, are obtained throughout the area estimator of our tangled bosons, okay? So, and it means that I have to study how the momentum of inertia is reduced. And of course, like as we know from the basic course of physics, so we can calculate the momentum of inertia along z, y, and x, of course, and we can come up with the total superfluid fraction depending on which axis we are looking for, okay? And then, so essentially, we apply the worm algorithm. And the worm algorithm is basically a worm that goes up and down in the configuration system where one tail is, the worm is the one body density matrix, okay? So in this way, opening and closing, using very well-defined technique, we are able to sampling superfluidity, condensation, and all the global quantum quantity, okay? So I don't have enough time to explain quickly the path integral, but if you want, we can discuss at some coffee break, because I want to show you the result about the first model with soft core bosons. We are able to build again all the clustering on the sphere. So, and increasing basically the quantum fluctuation, because the kinetic term represents the quantum fluctuation. I skip everything connected to parameter, because the soft core interactions are something related to like a toy model, but we are able to study the super solidity. So increasing the quantum interaction, the quantum fluctuation, sorry, we can go from a perfect isolated structure to a super solid with super solidity with cluster. It means that there are clusters with particles that can jump from one side to another, okay? And they have superfluidity. They have final superfluidity, and then if we increase again, the quantum fluctuation, the system, it's completely superfluid, okay? And here I put some information that maybe can represent better this kind of configurations, in the sense that here I take the azimuthal angle and the z direction, where you can see the formation of all this cluster on the sphere, okay? So let's study the superfluidity. We connect the superfluidity with a a 10-year-old article with Tommaso and myself and Thomas Paul, and we saw that in the strong confinement, increasing the number of particles of our quantum Monte Carlo, we come back with the result by Macri et al. Essentially here we have superfluid phase increasing this alpha parameter, which essentially is the ratio between the kinetic term and the interacting term. And then this region is a super solid region where superfluidity is between 1 and 0, okay? And then the system gets is isolated, okay? So essentially in this strong confinement, we really have the behavior of a super solid, as we already knew. For a weak confinement, we still have this cluster structure, although the fact that the surface is not small enough, there is a thickness that allow particles to delocalize not only through the Z direction, but also through the X and Y direction. So for that reason, the superfluidity here gets higher when the weak confinement is small, okay? So now I want to talk about something that maybe from an experimental point of view can be done, and I introduced the dipolar boson, okay? And here I increase the scattering length, okay? For a system fixing the density and also the radio, which is quite larger compared to the interaction that we are considering. And also I'm taking density from the Lambert experiments that we found in microgravity in a recent work. And the important thing is that when the scattering length is small, it means that the dipoles tends to remain on the equatorial zone here, and they try to collapse, okay? But they are not able, of course, because I impose a scattering length small but big enough to make the system forming this kind of structure in the equatorial zone. And the superfluidity, it's quite small. It's basically related only to the superfluidity of the patches here. But as soon as I increase the scattering length, the system starts to be super solid along the equatorial zone. And this has been obtained by looking at the superfluidity along the Z direction. Okay, I'm rotating the system in that way. And I have still a small amount of superfluidity along Z and Y. But then when I increase further A, I have this interesting ribbon, which is superfluid. Okay, it's not super solid. I don't have the formation of a structure, but the ribbon form a superfluid region only around, again, the equatorial zone. And we have two different signals of superfluidity. Okay, along Z here, it's still higher than X and Y, but that means that the system is start to become more and more superfluid. Of course, when I increase again and again the scattering length, the system becomes superfluid, as I showed you before for the soft core model, and basically the dipolar interaction is not working anymore for forming cluster. Okay, the last slides that I present is the problem of gravity, in the sense that we try to put gravity in our system, and we realize that the center of mass, in a way, of our structure goes a little bit down, okay, a little bit down compared to the previous configuration here, where we don't have any kind of gravity. But this structure still remain if you try, let's say, to do an experiment in the lab on the Earth. So the message, the interesting message here is that it's not important to put your experiment on the space, okay, around the Earth. And you see, another thing that I forgot to say before closing my talk is that only with hardcore our simulation find exactly the same result that I show you in the introduction of this project, and they just only everything fall on the south pole. Okay, so but it seems that with dipole interaction they can try to do this kind of experiment even on Earth. So I found this very interesting to propose. Yeah, so in this last slides, I would offer some outlooks. We are working in different directions. Of course, there is also the dynamics that are related to this system that are very interesting to study. And of course, because the quantum Monte Carlo is working on surface, on curvature, we are trying to study bosonic system on other more complex curvature that maybe might have any interesting also from experimental point of view. And of course, another thing connected to the supersolidity is the study of Goldstone modes, okay, which is something that we are doing. After my outlook, I think that I'm in time, and I thank you for your attention.
Hi, thank you for the talk. I wanted to ask, what's the significance of Ammann-Baker tiling specifically?
Say again, sorry?
What's the significance in the first part of your talk? You had a quasi-crystalline potential. What's the significance of having Ammann-Baker tiling in particular, as opposed to, for example, Penrose tiling, right? And whether somehow your results depend on that. We know, for instance, that the physics of strong interacting dimer model depends on whether you choose one or the other tiling. So does it make any difference for you?
Well, we chosen this because it's the most common tiling for creating quasicrystals. We haven't tried quantum simulation with other kind of quasicrystal, but I don't think that is going to change much. I mean, the idea that there are different neighbors for each side should generate again a region that remain with this kind of puddles, superfluids, which are related to a Bose gas. So I don't think that would change much. But we have to try. We have to try.
Okay, maybe not. Depends. In different interacting systems, it seems to make a difference sometimes. But okay, thanks for it.
Okay.
Thank you for the talk. I was wondering if you consider, so you show some results for different number of atoms in a certain sphere. What's the role of the curvature? Did you try to scale with respect to the curvature also? Or?
Yes. In fact, we did a lot of phase diagram, increasing, for instance, the radius. And at a certain point, more or less, we try some value of R, but for all R that we try, we still observe this kind of behavior. So a cluster which is not super solid, a super solid phase, and a superfluid. So this behavior is remaining. So, okay, so it seems that does not change much. So the super solid region tends to get closer and closer. So at a certain point, I will reach a limit where R simply generate a simple, I would say a flat situation mainly, yeah.
Maybe I'll ask one. So what's the signature of these supersolids in your calculations? I mean, is this density correlation profile is the
One is this, and the other one is the fact that superfluidity is not one. So if the superfluidity is unitary, the system is completely superfluid. If this superfluidity is between 1 and 0, and there is this cluster formation, okay, you can define superfluidity essentially in two ways. So there is the Andrew Lifshitz idea where you have delocalization of defect throughout the system, and also, and there is this one that we are using, that is the gross supersolidity, which is the one that many people are working in dipolar system. So you must have clusters of bosons where there is fine superfluidity, and Legged proved that this superfluidity in this case must be less than 1. So because you breaks the invariational symmetry of the system.
Other questions? I think everybody is looking to go for coffee, so.
Thank you. Thank you.
Join me in thanking both.